Thank you for the introduction. I suppose that he presented me. Yes, this, okay. So let me, first of all, thank Professor Belousov for inviting me here at the MIT and for giving me the possibility to deliver such a seminar and for his very kind hospitality. So, I'm Roberto Grimaudo, I'm a PhD student, third year PhD student of Palermo, the University of Palermo. My supervisor is Professor Messina, who is here, present. And, okay, in this seminar, I talk about, as you can see from the title, time-dependent Hamiltonian models for 1 qubit and for interacting qubit systems, in particular for 2 qubit systems. In my PhD, I have been engaged in the study of general time-dependent quantum dynamical problems, so time-dependent Hamiltonians. In particular, we study, our attention is devoted basically to time-dependent Hamiltonians describing quantum spin models, specifically spins, physical systems, microscopic physical systems describable by time-dependent Hamiltonians when the spins are subjected to time-dependent magnetic fields, time-dependent fields that we treat classically. So, can you hear me? Good? Yes? Okay. So, the outlines of the present talk are the following one. We will see, first of all, both the physical and mathematical relevance of the study, to study the dynamical problem of a time-dependent Hamiltonian models, so for a two-level system. We will see the milestones, actually, the two most important exactly solvable models for a two-level model subjected to a time-dependent Hamiltonian, and which are the Rabi and the Landau-Zener, or better, Landau-Majorana-Zuckerberg-Zener model. And in the meanwhile, I will show you some results that I got during my PhD about the generalization, let's say, in a certain sense, of the Rabi model, and about the application of the knowledge of the Landau-Zener solutions for a more complicated dynamical problem, that is the one of 2 interacting qubits. So, let us start by defining what is the general time-dependent Hamiltonian for a two-level system. We can write it in this way. We have a general superposition of the 3 Pauli matrices with time-dependent complex, in general complex valued functions. In this case, this is real. They are real. The matrix representation of this Hamiltonian in the basis of sigma z is the following one, where this parameter omega is expressed here in terms of omega x and omega y. Well, we know that actually such a kind of Hamiltonian can describe, in general, a spin 1/2 particle in a time-dependent magnetic field. The Hamiltonian, the time-dependent Hamiltonian of such a system can be written in this way. Here, of course, we have the spin angular momentum operator for the spin 1/2, and proportional through these 2 quantities, and this is giving the magnetic moment, and we have the magnetic field, which can be, of course, in general, time-dependent. So in this case, by putting these parameters, we can write, of course, the general time-dependent Hamiltonian in this way. But of course, we know that actually this is the spin 1/2 particle immersed in a time-dependent magnetic field is just one physical system describable by the time-dependent two-level Hamiltonian. Indeed, as we know, in physics we have a lot of physical systems which can behave effectively like a qubit, that is, as a two-level system. For example, these 2 physical scenarios are the most important ones. Actually, we have, for example, we can have ions or atoms trapped in a cavity or in an optical lattices. And we know that generally an ion or an atom in general is an n-level system, so we have a lot of level system, energy level system. But by sending laser fields, actually, I don't see the pointer, sorry. No, maybe, okay. No, maybe. Okay, well, so we can send by laser fields, I mean, just to couple two energy levels of our ion or our atom, so that it behaves like a two-level system. So in this way, we are able to produce experimentally an effective two-level system, or that what we can call qubit in general. The other physical scenario is also important, which is the one concerning quantum superconducting circuits. For example, here you have a very basic scheme of what we call a qubit, a charge qubit. Also in this case, this circuit, this very elementary circuit, is in general an n-level system, but under appropriate experimental conditions that is governing, setting appropriately these parameters, EJ, which is the energy of the Josephson junction through which we can construct such the charge qubit. This is the flux, external flux, and this is the voltage. Thanks to these parameters, we are able to reproduce effectively a two-level system. So this system behaves effectively like a qubit. This is very important. Why? Because, of course, in this scenario, we can have easily architectures in which we can construct an array that is a system of interacting qubits. Indeed, this is the most maybe important scenario, the most important candidate to generate what we can call the building blocks for a future generation of a quantum computer. We know that IBM in January 2009, this year, 2019, so this year, presented the QSystem-1, which is let's say a prototype of a quantum computer based exactly on 21 charge qubits, like the one seen before, even if, of course, that qubit is a very basic qubit. Now there are some more complicated architectures, but this is not the scope of the seminar. But what is important is that these are effective quantum systems behaving very well for quantum computation and quantum information tasks. Of course, I said before that we can call this a prototype of quantum computer because we know that a lot of efforts are still necessary, because we know that these machines work very well at very low temperature. Indeed, one of the most important issues that we have to face with is the interaction of our quantum system with the surrounding environments. The surrounding environments, we know that disturbs the dynamics of our qubits, and so it destroys the coherence, which is the most important physical feature, the most important feature of quantum system that we can exploit to do quantum computation and quantum information protocols. Okay, so we saw actually why, from a physical point of view, how important it is to study the dynamics of a single two-level system or interacting two-level systems, because their application, we have a very important application, most of all in quantum information and quantum computation fields. But we see now the mathematical relevance also for studying such a dynamical problem. Indeed, here we have again the two-level time-dependent Hamiltonian, and we can write the well-known Schrödinger equation, which can be written in this way. Maybe you are, for sure, you are familiar also with this writing. In a certain sense, this writing is let's say, more general, in what sense? That here, of course, we have to specify an initial condition for psi, so we study the time evolution of a precise initial condition of our system. But in this case, we see that here appear only the Hamiltonian and the time evolution operator of our system. So this is, here there is the dynamics of our system. So here we have not to specify the initial condition. And through this operator, which is the time evolution operator, we are able to find the time evolution of all possible initial conditions. So in this sense, it is more general. So if we solve such a Schrödinger equation for U, we solve in a certain sense the whole dynamics of we know the whole dynamics of our system. So from now on, we concentrate on this Schrödinger equation. This is the Schrödinger equation for the time evolution operator, and we know that when the Hamiltonian here, U is ever time dependent, of course, but Hamiltonian we know that could be time independent or time dependent. When the Hamiltonian is time dependent, we know that the Schrödinger equation becomes in general very, very hard to be solved. We know that just the formal solution for U is very complicated, and it involves we know the complicated Dyson expansions. But actually, we don't need of these of such a writing. Why? Because for our two-level Hamiltonian, we know from the group theory that the time evolution operator solution of this Schrödinger equation, of this dynamical problem, has a special structure, which is the following one, depending on just two parameters, A and B, which are in general time-dependent complex-valued functions, satisfying such a condition because of normalization reasons. Okay, so we have the matrix representation of our time-dependent Hamiltonian. We have the formal representation of the time evolution operator, so we can write easily from this equation this system of two coupled linear differential equation in A and B, depending on the Hamiltonian parameters appearing here. So these initial conditions for A and B are due to the initial condition U0 equal to 1. Okay. So what is very interesting, in my opinion, but maybe in general, it is the fact that this system of two coupled differential equation, linear differential equation, actually cannot be solved in a general way, in general terms. So what does it mean? It means that if we leave the time dependence of this Hamiltonian parameter completely general, so if we not specify, we are not able to find analytic solutions, so we are not able to solve this system. So what we can do at our best is to find specific scenarios. That is, it means to find specific time dependencies for these Hamiltonian parameters in such a way that we are able to find exact solutions for A and B, and so to find exact solution for this Schrödinger equation. So it means that we need to choose a specific Hamiltonian, so which is from a physical point of view also interesting, because we are interested in a specific physical scenario, physical problem. So in that case we have specific time dependencies of our Hamiltonian parameters, and in that case we can solve or not, but also in that case it is not in general easy to solve such a problem. Indeed, we will see why. A third point to be stressed, to be pointed out, is the following one. Actually, this manifests the interest of this dynamical problem both from a mathematical and physical point of view. Why? Because if we are interested in a certain sense in the same problem, the same physical problem, a time-dependent problem, we have the same Hamiltonian, but for an n-level system, so a spin j with value of j greater than 1/2, the Hamiltonian, of course, is subjected to a time-dependent magnetic field. The Hamiltonian can be written formally in the same way. Here we have now the spin j, spin angular operators. But what is interesting is that this dynamical problem, which is very more complicated than the previous one, the two-level system one, the solution of the time evolution operator, sorry, for this problem can be written, you can see above, can be expressed in terms of, can be expressed, the time evolution operator of this problem can be expressed in terms of A and B, which are the two parameters we had before. That is, these A and B are the solutions that we can find by solving the two-level problem. So it means, what does it mean? It means that if we want to solve such a dynamical problem for an n-level system, a spin J subjected to a time-independent magnetic field, it is sufficient to find the solution of the two-level dynamical problem to solve this problem. So when we solve the two-level problem, we solve the same problem, but for a generic n-level system. For example, for a three-level system, we have the structure of the time evolution operator here. You see that it depends only on A and B, and this is for the five-level system. Okay. You see that also, maybe you cannot see very well, but it depends only on A and B, you can be sure. Of course, you notice that the structure of this time evolution operator becomes, of course, more complicated for n-level, for when we increase the dimension of our system. But of course, what is important is that solving, again, the two-level dynamical problem, we can find such very complicated, yes, but we can find, of course, these time evolution operators if we are able to solve the two dynamical problem, which is not in general easy. Okay, if you wonder what these results stem from, we know that these results stem from the group theory. The mathematical reason is that such Hamiltonians minus mu scalar b has a particular symmetry, which is the SU2 symmetry. The time evolution operators related to such Hamiltonians are the one we saw before, for example, and so they are the group, they are the elements of the SU2 groups, and so they have the same symmetry, and this is why we can reduce the n-level time evolution operator to the two-dimensional one. Or better, we can represent the n-level system through the representation of the smaller, simpler case, which is the two-dimensional one. The group theory is a very elegant and a very important theory in mathematics, but very important also in physics, whose basis as given by Évariste Galois, which is one of the most important, maybe, geniuses in mathematics, because he developed the basis for such a theory when he was only 20 years old. Indeed, he died at 21 years old due to a fatal duel, due to maybe unlegitimated love affairs, but this is another story. So we can go now to see the first case, as I said before, the first most important case maybe of a two-level system governed by a time-independent Hamiltonians whose dynamical problem can be exactly solved. This is the Rabi model, whose Hamiltonian can be written in this way. We see that we have these constant parameters, and we have a time dependence due only to phase factors. From a physical point of view, these Hamiltonian represent a spin 1/2 immersed, subjected to a time-dependent field, which is precessing around the z-axis, okay? Like such picture recalled in a certain sense. So we have such a time evolution of our magnetic field. What is important is the following fact. Rabi was able to find the exact solution of this problem thanks to a very simple but at the same time very brilliant idea. That is, it is easy in a certain sense to understand that if we if we move to the frame rotating with the magnetic field, of course in this frame the magnetic field results time independent, is constant. So this is the trick used by Rabi. Indeed, he wrote the Hamiltonian in this rotating frame, rotating with the magnetic field, and in this case we see that we get a new Hamiltonian, but we see that we have only time-independent parameters. We have a redefinition of the magnetic field. In this case, we have magnetic field along the 3 direction. In this case, we have only Z direction and X direction magnetic field. But what is important is that in this case, in this frame, we have a time-independent Hamiltonian. And in this case, so we are able to find very easily the solution of the dynamical problem. And then we can come back to the laboratory frame, and the solutions of A and B of this dynamical problem can be written in this way. So we see that they are not complicated, but actually without these phase factors, they are the solutions of a time-independent Hamiltonians with the same Hamiltonian, of course, and this phase factor stems from the fact that in this writing we are in the laboratory frame, so not in the rotating one. But of course, the mathematical solution is very important, but what is very important in the Rabi problem is the fact that we can write, so we know analytical, yes, we know the exact dynamics of our system, so we can, for example, write the Rabi transition probability, that is the probability to find the system, our system in the upper state when it starts from the lower one. Okay, it is a time-dependent, of course, transition probability, and it is sinus, and the amplitude is this one. We see that it depends on the Rabi frequency, written in this way, which in turn depends on the so-called tuning, which is this quantity. And very important is the fact that when the tuning is equal to 0, we have the so-called resonance condition. That is, we have the maximum amplitude, reported here in blue line, we have the maximum amplitude for the transition probability. That is, there are time instants for which we have the maximum probability so that our system can accomplish this transition. Okay, because thanks to this condition, of course, this amplitude is equal to 1. So it means that our system in this resonance condition acquires energy from the fields, make the transition, and then comes back to the lower energy level, and so on in time. So when it comes back to the lower energy level, of course, it emits a photon, emits signal, and this is a physical effect, important physical effect at the basis of one of the most important techniques, not only in physics, but only in other fields, which is the Nmr technique, that is nuclear magnetic resonance technique, which is useful, for example, we know in medicine, for example, to scan our body and to detect some tumors. So this is the physical effect at the basis of this very important technique. So from a mathematical physical point of view, it is a very simple model, a very simple, let's say, study, but we see that it is at the basis of very important applicative technique. So this is the important, just to show the importance to study also these very simple time-dependent problems. So now I want to show a possible generalization of these results I got during my studies. Generalization, why? Because we wrote actually the same Hamiltonian. This is the general Hamiltonian of a two-level system, but rewritten in a new way, very similar to the Rabi one. We have this time we have a time dependence here, and here we have a general time dependence, not Ni0 t, but just a general time dependence. So in this case, the magnetic field is not precessing, but can have a very complicated time evolution. But we have been inspired by the procedure of Rabi in the sense that we want we wanted to write such an Hamiltonian in the frame moving with the magnetic field. Of course, I repeat, it is not the frame precessing around the z-axis, but in general, it is a general frame following the magnetic field. In this frame, we see that the Hamiltonian can be written in this way. It is very similar to the one of Rabi, but this time we have time dependencies here. So in this case, we are not able again to find a general solution of our problem. In the Rabi case, we get a time-independent Hamiltonian. Here we have a time-dependent, general time dependence. But what is important, and very interesting, is the fact that in this, like in the Rabi case, here we can recognize the expression of a time-dependent detuning in a certain sense. So it means, we saw before that detuning is fundamental to reach the resonance condition. So in this case, it means that if we put 0 at any time this parameter, of course, we get what we called a generalized resonance condition. It's important. Why? Because if this term is 0, of course, we don't have this term. We have only this, but this is a very simple Hamiltonian. We can solve exactly the problem, and so we can write the new Rabi transition probability. We see that we have amplitude 1 because we are in resonance condition, so we are in the case in which the system make a full transition between the two levels. But this time, of course, we have not a constant frequency, but this time the argument of the sinus depends on the integral of the modulus of the transverse field of small omega. So what does it mean? It means that depending on the time dependence of the transverse field, small omega, we can have different regimes like showed here. So for example, just to show, we calculated, for example, a monotonic regime, an oscillatory one, and a mixed one. These regimes, of course, are related to different, we see, time dependencies of the small omega parameters. It is interesting to note that in the first and the third case, even if we have qualitatively similar time dependencies, actually we get very different time evolution for our transition probability. This is due to the fact that in this case we are finding the analytical, the exact expression of the transition probability. So very small differences can cause a very big difference in the transition probability. If you are interested in get other aspects and to go in depth in this study, you can read the paper in which we reported such an analysis. So let me go now to the second important, very important model, which can be whose dynamical problem can be exactly solved, which is the Landau-Zener, well known as Landau-Zener, but actually it is the Landau-Majorana-Zuckerberg-Zener, because these four scientists, very big scientists, get the same solution in the same year, totally independently. So, but let us see, first of all, in what consists this model. Actually, we have the capital omega parameter of our Hamiltonian depending on time in this way. So we have a linearly dependent field on the z direction, and we have a transverse field on the x-axis, which is constant. Okay, this is the very important energy diagram of our two-level system. These two lines, are the time dependent eigensolutions of the sigma z operators. They are time dependent, evolved in this way in time because of the time dependence of the linearly varying magnetic field. Okay, so this is along z, and so the eigenvalues of sigma z evolve in time in this way. These two instead are the instantaneous eigensolutions of our Hamiltonians, the time dependence of the eigenvalues of time dependent eigenvalues are the time dependent eigenvalues of our instant eigenvalues of our Hamiltonians. What is important is the following fact: is at minus infinite times, actually these eigenvalue coincides with the state 1 of sigma z, of the sigma z operator, and at plus infinite times it coincides with the second eigenvalue of sigma z. So what does it mean? It means that if we start, for example, from 1 at minus infinite, if we vary very slowly the magnetic field along the z-axis, actually our system follows time by time these will be at any time in these eigenvalues, thanks to the fact that the dynamics is adiabatic. So it means that at plus infinite time, our system will be in the level 2. So we are producing a perfect transition between the level 1 and the level 2 of sigma z. This dynamics is well described by this formula, which is the Landau-Zener Formula. We see that it depends on the modulus of the transverse fields squared and on the slope. This is called the slope of the z magnetic field. We see that when alpha is very, very small, so when the field varies over time very slowly, this exponent is zero, this exponent is infinite, so this term is 0, and the probability is 1. So for in adiabatic conditions, the transition probability is exactly 1. But of course, maybe you are thinking about the fact that actually it is an ideal model, and indeed it is, in the sense that as we can see here, of course, this formula is valid going from minus infinite times to plus infinite times. So from a physical point of view, of course, it has no sense from a physical point of view, because it means that our procedure, in a certain sense, is an infinite procedure. So, but actually, if we are interested in studying the same dynamical problem, but for a time-restricted time window, actually also in this case we are able to find the exact solution of the dynamical problem. The solution is due to Vitanov and Garraway, found in 1996. The paper where you can find the solution is this, on PRA, and the solutions can be written in this way. We see that actually they are very complicated solutions. I wrote them just to show you that also very simple dynamical problems for a two-level Hamiltonians like the Landau-Zener one, because actually it is simple from a physical point of view. We have a simple field on the z-axis and a constant field on the x-axis. So very simple also to understand from a physical point of view, but this very simple physical problem actually admits solution, but they are very complicated. So just this shows us how it can be very difficult to find solutions also for very simple problem when the Hamiltonian is time dependent. Okay, so let me go now to the second, in a certain sense, second and final part of this seminar, which regards, in a certain sense, the core, the heart of my PhD. Indeed, this is actually, in a certain sense, the question which Professor Messina posed me at the beginning of my PhD. That is, how actually can we exploit the knowledge of solutions for some dynamical problems of a single two-level system for more complicated systems, for example, for interacting spin systems. So, of course, the Hamiltonian, let us think about the fact that the Hamiltonian of two interacting spin 1/2, for example, has no an SU2 symmetry, so we cannot exploit what we have seen before. So actually, in this case, another strategy is necessary. What can it be? Actually, the method, the approach we used is based on three, let's say, on 3 steps. So the first one is to study the symmetries of the Hamiltonian operator in such a way to individuate constant of motion, allowing us to identify a subspace, invariant Hilbert subspace, here represented by these squares. These are, let's say, independent orthogonal invariant Hilbert subspace. So at this point, we search those subspace in which we can recognize an SU2 symmetry. So in this case, we are able, for example, to write, as we saw before, to write the solution of, at least the formal solution of our dynamical problem, because we can describe effectively the dynamics of our system in terms of a spin j subjected to a magnetic field. And so, at least in one or some of these subspaces presenting an SU2 symmetry, we can of course find exact solutions of our original dynamical problem, which is the problem of interacting spins. Well, of course, it is very simple as approach, but of course it could be complicated to be realized in a certain sense, because you can have very complicated systems. But just to show a successful case, this is the first model I studied. We have two spin 1/2, spin 1 and spin 2, subjected to two local magnetic fields, time-dependent magnetic fields, and they interact through these, we can call it anisotropic Heisenberg interaction, but this is not important. We have these interaction terms. The matrix representation of this Hamiltonian in the basis of sigma 1z, sigma 2z is the following one. The matrix representation in this case is very important. Why? Because it is easy to see easily the existence of two subdynamics. We see the external blue one and the internal green one. These are two subdynamics related to the existence of two invariant Hilbert subspaces. These two subspaces are two-dimensional subspaces. So within each subspace, we can describe our two-spin system in terms of just one spin, in terms of a two-level dynamics. Indeed, we can write, for example, an effective Hamiltonian for the external dynamics and an effective Hamiltonian for the inner green dynamics. They can be written, of course, we derive analytically such two Hamiltonians through the symmetry-based approach. So it is very important. Why? Because it means that in this case, we can reduce the solutions of our original dynamical problem into the solutions of two independent dynamical problems, each of which is a dynamical problem of a single spin 1/2, so a single two-level system. So, for example, it means that in this case we are able to write formally the solution of our original system. We can write the formal solution of a two-level system for the external dynamics and the formal solution of a two-level system for the inner dynamics. These A minus, B minus are different in general from A plus and B plus because these two subdynamics are completely independent. But of course, I stress the fact that actually here we have fictitious spin 1/2. Actually in these two subdynamics, actually the real spin 1/2 are both involved. Indeed, so we can now analyze, for example, a specific scenario, a specific time-dependent scenario. For example, we can we studied such a model, such a scenario in which we have a magnetic field on the first spin 1/2, linearly varying on time, like in the Landau-Zener case, and the second spin is completely free from any field. So, in this case, of course, our two-level effective, fictitious, time-dependent two-level Hamiltonians are actually two Hamiltonians of Landau-Zener Hamiltonians. Indeed, we see that here thanks to the presence of omega 1, we have the Landau-Zener longitudinal field varying linearly on time, and this is actually the fictitious magnetic field, constant transverse magnetic field, the same of omega 0 in the model of Landau-Zener. So it means that for these two effective Hamiltonians, actually we have a transverse field, the presence of a transverse field. The role of the transverse field is played by this expression of the two coupling parameters. And this is very important. Why? Because in the model of the two spins, actually we see that we do not have a transverse field. Okay, the two real spins are not subjected to a transverse field, but in the effective Hamiltonians, actually we have a transverse field. So what does it mean? And it is due to the presence of the coupling existing between the two real spins. So it means that in this case we can write the Landau-Zener transition probability for the two subdynamics, and so here we have the transverse field and here we have the slope, so we can write the Landau-Zener transition probability in the two cases, and they appear in this way. We see that here we have the slope of the field, and here in general we have the transverse field, but in this case we have the coupling between the two spins. So this is why we speak of a coupling-based Landau-Zener transition. Actually, this is a physical effect we found in a certain sense by this analysis. Coupling based because, of course, the Landau-Zener transition are possible only when a transverse field is present, but for our two spins, no transverse field is present, but this role is played, as I said before, by the existence of the coupling, and so the Landau-Zener transition are possible thanks to the presence of the coupling existing between the two spins. But the very interesting thing is also the applicability of such a physical result, of such a physical effect. Indeed, we can, I show you now that we can generate maximally entangled state thanks to this, between the two spins, the two spin 1/2, thanks to this effect. Indeed, we studied the asymptotic concurrence. The concurrence is a measurement, a theoretical measurement for the entanglement between the two spins, and it can be written in terms of the two probability, Landau-Zener probability we found before. And if we plot, for example, the first curve against the parameter beta, we have this blue curve. We see a very important thing, that it exists a value of the parameter beta for which we have the maximum value for our asymptotic concurrence. So it means that this value is exactly about 0.1. So it means that by setting the parameter beta equal to 0.1, we are able to produce the possible maximum level of entanglement between the two spins. Indeed, this is what we have proved by studying the time evolution of such initial condition. We start from a zero entanglement. Okay, here we have the concurrence against the time. And we see that setting beta equal to 0.1, for very large times, we get the maximum possible value of the concurrence, that is 1. Indeed, in this case, the system is reaching this maximum entangled state, which is a Bell state. Indeed, we prove also that by setting beta with other values, we see that actually starting from the same initial condition, we get other values for our concurrence. In this case, we get again 0 because in this case the system is reaching this state. So we see that the beta parameter is fundamental, of course, for the time evolution, and but it can be can be manipulated by the experimentalists in order to generate maximally entangled states. A very interesting, curious thing is the following. Actually, when we have large values of beta, we are in adiabatic conditions. Small values of beta actually realize a non-adiabatic dynamics. So it means that actually the generation of maximally entangled states for our system require a non-adiabatic dynamic with respect to an adiabatic one. This is very curious, very interesting. This is to the fact that we have to realize a Landau-Zener transition probability which asymptotically reach the value 1/2 and not 1, but this is more technical, but we can go on. If you are interested also in this analysis, you can read our paper on PRB, which is this, about UC coupling assist and Landau-Zener transition. And here you can find the same analysis, but for a more complicated system, which is the one of two interacting Q-treats, that is the one of two interacting three-level system. This is just to show that I showed you, of course, our method, our approach in the case of 2-spin 1/2, but we can apply successfully the same model, the same approach, sorry, the same method also for more interesting from a physical point of view and for more complicated systems. So we studied also n-level system, n-spin problems approached by with the same method, and we also in that case we were able to find analogously exactly solvable, exact solutions. So let me conclude by summing up. We see that we saw that the study of the dynamical problem of a two-level system is very important, both from a mathematical and physical point of view. Of course, for us, we are physicists, it's very important from a physical point of view, because we saw, for example, in the Rabi case, we can find some physical effect which could turn out very important for application, like Nmr in that case. And we saw indeed in what consists the Rabi model and the Landau-Zener one, which are the two most important, two most famous exactly solvable two-level dynamical problems. And we saw actually a possible generalization of the Rabi model and the application of the Landau-Zener solutions to a more complicated system, which is the one of two interacting qubit systems. So, to conclude, I want to stress that actually I showed you, of course, let's say ideal systems, in the sense that here we don't have, for example, the interaction of our quantum system with the environment, which is very important, because we saw that, I told you before that this is fundamental to study real physical system useful for quantum computation and quantum information. Actually, I didn't show, but we are able, for example, to find some solution also in this case. That is when, for example, we consider the interaction of our system with a surrounding environment in actually two ways. For example, the first one is when the magnetic field has a noisy component, that is a component which fluctuates randomly in time, and the other one is when our so in this case we describe in a certain sense effectively the interaction of our system, quantum system, with the environment, and the other one is to consider instead exactly the interaction of our system, a quantum interaction, let's say, with a quantum bath, for example, made of quantum harmonic oscillators. So for special conditions, so in some cases we are able to, in a certain sense, to exploit our approach in order to find exact solutions also in that case. But of course, in such cases, analytical solutions to be get becomes very hard. So in that case, we are approximated solutions. In this case, instead, we saw only exact analytical solution. So I think that I have spoken enough, so you are enough bored. So I thank you for your kind attention. Thank you.
So, in case of 5-level system, I just want to understand why you have only 2 parameters, A and B, describing the 5-level system.
Yeah.
2 parameters. Why not 3? Why not 4?
Yeah.
What kind of approximation is that?
No, there is no approximation actually in this case for this result. Actually, it's due to the. I know that I went a bit far, but because I don't want to give detail about the group symmetry. This is due to the fact that actually for an n-level system, actually the more general Hamiltonian belongs to the SUN symmetry, the SUN dynamics. The general n-level Hamiltonian is the generator of the SUN group. So in this case, we have n parameters. Okay, but in this case, for such Hamiltonian, describing, for example, an n-level system as spin j subjected to a time-dependent field, this Hamiltonian has not an SUN symmetry, but an SU2 symmetry. So it means that this Hamiltonian is the generator of the SU2 group. And in such a case, we can reduce actually the study of our problem to the case of the smaller one, because the two-dimensional one is the simpler, but also the simpler representation of this group. So this is why we can reduce the n-level system to the two-dimensional one, because we can represent the group, the symmetry of the group just with the two-dimensional one. Of course, we cannot do the same, for example, in the three-dimensional case. Of course, in the SU3, I mean. For example, if we consider a 3-level system, but with an SU3 dynamics, so it means that in this case, our Hamiltonian cannot be written in this way, because this is a writing linear in the spin operators. For example, for a 3-level system, we can have the squared of Jx, Jy, and Jz, for example. In this case, of course, the symmetry is not SU2, but is SU3. In this case, we need of at least 3 parameters. Also in this case, we can consider an n-level system with an SU3 symmetry, and in this case, we can reduce the problem to the 3-dimensional case, which is the simpler representation of the SU3 group. So it is a mathematical property stemming from the group theory. So you can reduce in this, depending on the symmetry of your group, you can reduce to the simpler representation of your group, which for SU2 is the 2-dimensional one.
So n-level system can be considered using just 2 parameters. Well, mathematically this may somehow be justified, but what physics is behind it?
So, of course, you should keep in mind the fact that, for example, this is. For example, a three-level system. You see that in the Hamiltonian, actually, we have 3 parameters, the 3 magnetic fields along the 3 direction. The 2 parameters are related to the time evolution operators, okay, to the time evolution operator. Here, you need only 2 parameters in the sense that you can write the evolution operator in terms only of A and B. Okay, so these are the solution of the 2-level system, but of course from a physical point of view it means that of course this is not the same of the 2-level system. The parameters, the solution for A and B are the same, but of course here appear A squared, for example, in the 2-dimensional one appear A, so of course something changed, or better, a lot of things change, because when you from physical, actually, if you study, for example, the initial condition 1, 0, 0, of course, you get the time evolution which involve these three terms. No, sorry, these three terms. Of course, it depends on the dynamical problem you consider. Of course, A and B can have a precise expression, and you have so your amplitude for your state. So I don't know if I understand your question, but actually it is different because this time evolution operator is expressed in terms of A and B, but of course it is not the same. The dynamics, of course, it is not the same to level 1. Actually, just the mathematics can be reduced to the level, but of course the study of the dynamic of the physical problem is completely different.
Well, and another thing I wanted to
Yeah.
ask you. When you considered closer to the end of your report, coupling between two spins,
Yeah.
do you have a solution for the spin coupling in the absence of magnetic field?
In the?
When the magnetic field is 0, is there any spin-spin coupling?
I take. Okay. You mean here? We have, so.
Does your solution include any spin-spin interaction?
No. Actually, what we have seen actually is related for these interaction. Actually, we can, there is another paper, the first one actually on PRA, where we have a more complicated model in which we have also all other two terms, interaction terms, involving xy and yx. But in this case, the Hamiltonian has the same symmetries. But of course, if you insert here, for example, a term, an interaction term, for example, sigma 1x, sigma 2z, of course, in this case, you lose your symmetry, and so in this case, we have no longer these two independent orthogonal subspaces, and so we cannot apply our methods. So this is possible. What we have done is possible only with this interaction term, because the interaction in general, the form, the expression of the Hamiltonian is fundamental. Its symmetries are fundamental, of course, to individuate such subspaces. If we change a Hamiltonian, of course, the subspaces change, and so you have to change the analysis, and of course, the physics change drastically.
So that's a kind of approximation.
Approximation, it means, yes, of course, it is not the most general it is not the most general operator for two interacting spins, yes, but we know that a lot of physical systems, or better, actually, here we have an anisotropic Heisenberg interaction. Actually, a lot of physical systems interact with an isotropic Heisenberg, so when these parameters are all equal. So in our case, we have more parameters than what is necessary in a lot of physical systems. For example, for trapped ions or atoms, you can succeed in producing such an isotropic, or also for qubits. It is more common, the isotropic, than anisotropic one. And we found also such kind of interaction also for in systems of binuclear units. We have systems, crystals, in which we have binuclear units, so pair of nuclear spins interacting from each other, and we have a lattice of these. And we see that, for example, there is a precise molecule that now I don't remember, in which the symmetry is the SU2 symmetry of this binuclear unit, and the SU2 symmetry, the interaction between the two spins under the SU2 symmetry, is described exactly by this Hamiltonian. So it is, yes, an approximation in the sense that it is not the most general one, but from a physical point of view, it's we find a lot of physical systems described by such an Hamiltonian.
Okay, thank you.
Thank you.
More questions? We already discussed today. Okay, maybe I have a question to say. I guess this Hamiltonian may, yes, it seems, can describe And then, in general, it is known how to make internal state, Bell state, in a standard fashion.
Mm-hmm.
Did you analyze in your way with this non-adiabatic mode? Can you produce this internal state faster than with a standard technique?
No, actually not.
Much faster.
Actually not.
Might be quite interesting.
Maybe yes, because
Produce
yes, and
without distortion.
yes, you are completely right, and thank you for this observation, which is very interesting. Actually, this is one of the outlooks we have in mind, because actually in the paper I showed you, we concentrated just in highlighting the physical effect, which is the coupling-based Landau-Zener effect for two spins, and so in that case we wanted to just highlight such an effect and to study some possible applications, but of course this could be a very interesting outlook, so that is to understand experimentally from a practical point of view how much this model can be, this effect could be interesting. Yeah. Thank you.